water solubility, another issue. The alcohol can participate in hydrogen bonds with water in two ways. It can act as a hydrogen bond donor by having its hydrogen attracted to the non-bonding pairs of electrons on water, or the non-bonding pairs of electrons on the oxygen and the alcohol can have the same interaction with the hydrogens from water. Alcohols are both hydrogen donors and hydrogen acceptors in hydrogen bonding interactions. Do you understand the distinction? The hydrogen bond donor provides the hydrogen. The hydrogen bond acceptor provides a non-bonding pair of electrons to interact with the hydrogen. And alcohols do both. Interestingly, let me ask you a question. Digress just a little bit. Let's get this message going off here. What about this guy? The dimethyl ether we saw in the previous slide. Does it hydrogen bond? No. Not with itself, but what if I put water? Yeah, if I had an alcohol or water, then it can. It can act as a hydrogen bond acceptor. What that means to you is that ethers are a little bit, that they tend to get wet. They tend to have a moderate solubility in water, or they dissolve a little bit of water in them. And you're going to be doing a Grignard reaction soon. I can't tell you how exciting that is. Let's hope it doesn't rain on that day. But that Grignard reaction requires absolute bone dryness. And so we will buy special ether from a laboratory supply house that's been dried down so it's very, very dry and has a septum cap on it so that we can only access the ether with a syringe. And it's kept dry for the reason we're talking about right here. Water destroys the Grignard reagent. Ether stabilizes it. But since ether tends to dissolve water out of the air and a variety of other sources, you're going to need to make sure that your ether is extremely dry. And ether tends to pick up water because of these hydrogen bonding interactions. It acts as a hydrogen bond acceptor, but not a hydrogen bond donor. So ether molecules don't hydrogen bond with each other, but they do hydrogen bond with water and alcohol in that fashion. Look at the solubility. Up through about 4 carbons, tert-butyl alcohol, we've got complete miscibility with water. Isobutyl alcohol, about 10%, N-butyl, about 9%. And look how the solubility falls off dramatically as the hydrocarbon component becomes more. We're going to look now at a few common alcohols. Methanol is a great solvent. You can go to Home Depot and buy methanol. It's a good solvent for removing lacquers and varnishes from old surfaces. And usually what they'll do, if you buy a lacquer stripper from a hardware store, it's going to be a mixture of methanol and maybe some chloroform and maybe a little bit of acid. And the methanol and the chloroform are great solvents. They'll strip that coating right off. That's not, however, why it's called wood alcohol. Why is it called wood alcohol?
It's derived from it.
Yeah, the first methods for producing it involve taking wood chips or sawdust and heating it up to very high temperature without oxygen being present. If oxygen is present, then the whole thing just turns into wild configuration, big fire, it burns. But if you decompose cellulose wood without oxygen being present, methyl alcohol forms in pretty large amounts. And so the first methods for producing methyl alcohol were the decomposition at high temperature of wood products. And that's why it's called wood alcohol. Anymore, it's largely produced from petroleum and coal products and in the formation of something called synthesis gas. This stuff is really quite toxic. The toxic dose is about 100 milliliters, and of course that's based on body size. Toxic doses are usually in milliliters or grams per kilogram of body weight. And so if you're smaller, then the toxic dose is much less for a child. Yes?
Toxic dose mean it will kill you or just hurt you?
This is not a very good term. Normally what we talk about is something called an LD50. What does that mean? goes for 50% of those things. That gives you an idea of what is a common toxic dose in the sense of a lethal dose. Here, this probably means we start doing tissue damage, to the kidneys, to the liver, whatever. And this is a fairly common problem because a lot of people will have methyl alcohol in their garage or in the workroom, and kids see the word alcohol, and mom and dad are not around, and so they think they're going to try something that will be fun. And this is about twice as toxic as ethyl alcohol. By the way, the word intoxication has toxicity as a group, so both of them are dangerous and toxic. Ethyl alcohol, your body is better adapted to removing, using the liver, from your tissues and your fluids. Methyl alcohol, not so much so. When I oxidize methyl alcohol with liver enzymes and the natural protective enzymes, they actually produce formic acid, which is really nasty. If I do the same thing with ethyl alcohol, I produce acetic acid, which is vinegar. And so the body's defense systems, those enzymes that we find in the liver, turn ethyl alcohol into a relatively non-toxic end product, and it turns methyl alcohol into something that's really nasty. Causes kidney damage and very serious effects. Blindness, and a number of other things as well. This thing is used in fuel, in race. Interestingly, this alcohol fires can be extinguished with water, but hydrocarbon fires, you shouldn't. Why? What's up with that?
No soluble.
If I have a gasoline fire, what will happen if I splatter water on the gasoline fire? The gasoline does not dissolve in the water. All that will do is move the burning liquid into various places. It will just spread the fire. Does that make sense? But alcohol fire, because the alcohol dissolves in the water, you can extinguish it that way because you can dilute it to where it won't burn anymore. So alcohol fires can be put out with water. Don't do that with hydrocarbon fires. And that has the opposite effect. When I put alcohol in fuels, I get good emission characteristics, good octane ratings, but lower energy content. What do I mean by that?
It's going to be less carbon hydrogen, less carbon hydrogen bonds, right? Or less carbon bonds?
Yeah, if I look at ethyl alcohol, and methanol would be the same. This is ethanol, or ethyl alcohol. This thing is used in gasohol products, all the way up to about 85%. If you do some thermodynamic calculations with this, you'll find that this has about maybe 60% of the energy content that a comparable hydrocarbon will have. In other words, if this were ethane, it would have a lot more kilojoules per mole of energy that can be harvested from combustion. Why would that be? I'm asking a question I don't really expect you to know the
The
answer
carbon
to.
hydrogen, no? That always replaced the hydrogen, right?
Whenever we replace a hydrogen with an oxygen, there's energy released. So the ethyl alcohol can be considered a fuel that's already partially combusted.
Partially oxidized.
Partially oxidized. Does that make sense? And so some of the energy has already been extracted from the molecule. What would you predict then about acetic acid, which looks like this?
Way less.
Yeah, considerably less still. Every time I remove a hydrogen and replace a bond with a bond of oxygen, I take energy out of the molecule. And so acetic acid has got some energy for combustion, but much less than ethane and even much less than ethyl alcohol. Does that make sense? So, we get better octane ratings and lower emissions, but we don't get as many miles when we use alcohol in our fuel. And that's true for us. When we go into the winter months here, they start putting alcohol in our fuels, our gasoline. I don't know that you know that, but they do. And when our winter visitors are here and there's more cars on the road, they're trying to keep the emissions down. What that means, and you may have already noticed this, if you fill up the car, you're going to go fewer miles before you need to fill up again, because some of the fuel is not as high in terms of its energy content.
So, okay, between ethanol and acetic acid, which one is higher energy?
This one here.
That one's the highest because it's less oxidized.
Yeah, these two hydrogens have been removed to go here.
So methanol would be the lowest of all three.
Methanol actually would be probably less than ethanol, but still
But
pretty
more
good.
than.
This is
But-
the hydrogen.
Yeah, it's not as oxidized.
Okay.
Okay. By the way, and at the bottom bullet point there, alcohol fires are nearly invisible, and that's what makes them dangerous. If you toss a lit match into a can of gasoline, that's a problem. That's what I would want, because the compound is so full of energy that the reaction is so highly exothermic and dramatic, it's really dangerous. If you do the same thing with an alcohol, it won't do that. It will just form a little light blue, almost invisible flame over the surface of the liquid. You've seen Sterno. You've seen Sterno or fondue systems. You've seen that those flames are kind of hard to see, and that's what makes them a little bit more dangerous, is that they can be burning away and people don't know. And because they're hard to see. Flames are not really invisible, they're just hard to see. Ethanol, as opposed to methanol, is generally produced by fermentation of sugar and starches. What happens is the yeast produces ethyl alcohol as a byproduct until the ethyl alcohol content gets up around 12 to 15%, and then the mixture starts to become toxic for the yeast, and it starts to die away. If the yeast is the right type, or there are other bacteria there, the ethyl alcohol is oxidized further to acetic acid, and that's an issue for winemakers, because you don't want vinegar in your wine. And so you need to stop it at the right point where you've got an optimal amount of alcohol. And this would apply to beer as well. Okay, and for whatever reason, the mixture used for producing beer produces a lower percentage of alcohol. Now, beer also produces carbon dioxide, which means that the metabolism is going further, and you're actually getting all the way down to metabolizing the carbon dioxide. If I take this mixture and then distill it, that is the way to produce particles. So I can take, for example, a rye mixture, rye sugars, ferment it, and then distill it, and I get a rye whiskey, or bourbon, or brandy. Those are all hard beverages that are produced by distilling a fermented mixture. Okay? Rice produces sake. I can get a drinking seminar here, but each of the different substances, or each of the different sugar sources, is capable of producing a fermented form, and it can either be consumed in that form or distilled further to make alcohol. Interestingly, ethanol boils as an azeotrope. What's an azeotrope?
It boils at a lower temperature than the individual components.
Yeah, it's a constant boiling mixture of two components or more. They're tri-component azeotropes, but it turns out that water and alcohol boil at about 80 degrees, and that mixture will be about 95% ethanol and about 5% water. And so by distillation, we can't purify ethyl alcohol any more than 95%. In order to get it what we call absolute alcohol, we have to put a drying agent in there to dry down the water that came across in the distillation. When that happens, that's called an azeotrope. An azeotrope is a constant boiling mixture. By constant, I mean the mixture, the composition is constant. Not all liquids do this, but a good number of them do. In the back of the handbook of chemistry and physics, there's a whole table of isotopes like that. And if you're in a research laboratory and you're working with one of those, it's a good idea to be aware of those possibilities, because you might actually be trying to purify something you can't purify with distillation. Denatured alcohol, what's that?
Reason?
It turns out that it's pretty cheap to produce ethanol with your industrial methods, and because